Welcome back to my classes on fundamentals in transients this time. And we have looked at some of the basic things associated with transients. Now we go a little deeper and we choose the capacitor this time. Okay, capacitor has its own style of having transients. So we choose the capacitor first and then we'll go on to the inductor. Okay, so they both have, they are more or less duals of, with respect to each other in the process of being, in the process of the creation of the transients. And hence this particular slide is consolidating whatever we spoke about last time. It also tells us in depth as to how the transient how the transient associated with the capacitor can be analyzed. Okay? So time constant, as was mentioned before, is equal to tau as equal to RC. So it's normally measured in seconds. Okay? And then we have the capacitor, which has already acquired charges. Okay, now getting a circuit for discharging and discharging it out as discharging the charges out as a current as given by VCT is equal to E into E, that is the initial voltage that has been collected in the capacitor, multiplied by E raised to minus T by RC T, okay, or T by tau, minus T by tau. Okay. On the other hand, if a capacitor is going to charge from 0 to the full voltage of E, then the charging process or the transient can be explained as equal to VCT is equal to E into 1 minus E raised to minus T by RC or minus T by tau. Okay. So this is these are things that we have learned in our transient classes, and this phenomenon is continuously happening, be it in power system, be it in power electronics, be it in machines, or any aspects, any part of electrical engineering, okay, and also in electronics engineering. Moving on to another aspect wherein there's already some charge stored, okay, and then now switching is made to another situation. Then we are having two bits. One is, of course, whatever is already charged discharges, and then again, so if let's say if VC0 is the voltage that is already built up as a result of collection of charges, then VC0 into E raised to minus T by tau, where tau is equal to RC, and this RC remains constant for both, it remains the same for both aspects, that is for discharging. At the same time, what may happen is that the new source may charge the capacitor again. If it is in the same direction, then you add them together as equal to VC infinity. Why is it VC infinity? Because finally it is charged to a particular voltage when it opens out. So that VC infinity into 1 minus E raised to minus T by tau, where tau is equal to RC. Okay? And so both charging and discharging, especially charging, is associated with the current, and that current will be given by C into dVC by dt. Okay, whatever be the mode, is it a charging or discharging? Okay, so these are some of the aspects associated with some of the concepts that may be remembered for doing the problems that follow. Okay, so let's look at the first problem. So in problem number 1, we have a circuit wherein 11 volt pulse is delivered. The pulse is very short. It has a duration of 10 microseconds. And then we have a resistive network of 1 kilo ohm and 10 kilo ohm, where 10 kilo ohm is parallel to 11 nanofarad capacitor. Okay, so obviously that 11 has something to do. Okay, so let's read. 11 volt pulse of 10 microsecond duration is applied to the circuit shown in figure. Assuming that the capacitor is completely discharged prior to applying the pulse, the peak value of the capacitor voltage is what? Okay, so obviously the capacitor is getting charged as a result of this pulse. And how much does it get charged to? It gets charged to a total voltage as given by the time when the capacitor has opened out. Okay, so when the capacitor opens out, inside the circuit we have 1 kilo ohm and 11 kilo ohm. Okay, so or in other words, they share the resistors share the voltage of 11 volt. So we are having 10 by that is we are having 10 by 11 into 11, or 10 volt is now 10 volt of the pulse is now available across the capacitor. Okay, For how much time? Only for a time as equal to 10 raised to minus 6 or 10 microsecond. Okay. So and how does it charge? It charges as the final voltage that is possible, which is 10 into 1 minus e raised to minus t by RC. Okay. And what is minus t by RC? Because RC is tau. So for that, to calculate tau, what do? You short circuit the voltage source, and then you look from the capacitor. You see that the impedance, the resistance that is connected to it is the same as equal to 10 into 1 by 10 plus 1 or 10 by 11. Okay, so the time constant is very easily the same as equal to 1 by RC or 11. Okay, so all those aspects are known to you. That is, R is now the same as equal to 10 by 11, and C is 11 nanofarad. So all the 10 raised to minus 9, etc. come into the picture. So everything is written together as equal to the voltage, the maximum voltage to which the capacitor is charged is the same as equal to 10 into, as was mentioned earlier, 1 minus e raised to minus t by RC, where RC is tau, which is the same as equal to 10 into 1 minus e raised to minus t into, we are having we are having the time, that is 10 raised to t is the same as equal to 10 microseconds or 10 into 10 raised to minus 6. And what is RC? R is the same as equal to 10 by 11. And what is C? C is 11 nanofarad. So so when you put all these together, you can see that the capacitor charges only up to 6.32. By that time, the pulse is gone, and then the capacitor has to start discharging if it finds a circuit. Okay, so this is a very important application of the concepts that we studied in the previous slide, as also in the previous classes. Okay, we studied that the capacitor is getting charged, but it charges only until up to the time that the pulse is available. So that's the only difference here. Okay, so we move on to problem number 2. Here we are having a 20 volt being applied via a switch to a 10 ohm and a 20 microfarad in parallel to 10 ohms. Okay, so of course the switch is just being made, which means that there was a steady state. Okay, so let's see if anything else is given. In figure, the initial capacitor voltage is 0. So nothing more is given. The switch is closed at t equal to 0. The final steady state voltage across the capacitor. Okay, so finally what happens to the capacitor is that it gets opened out once it is filled with charges. Okay, so that's the reason why it gets opened out, because now it can't store any more charges, so it opens out. Okay, so once it opens out, there's an open circuit across 10 ohms. So 10 ohms and 10 ohms now become in series only now. Okay, and so 20 volt is shared, and that's equal to 10 volt. Okay, so it's when 20 volt is shared between two equal resistors, it's equal to 10 volt. Okay, so moving on to problem number 3. Circuit shown, switch. Okay, so now what is the circuit? There is a 10 volt source. The switch is going to be made, and then there is 3 ohms and 2 ohms across 2 ohms, just like in the initial problem. We are having a capacitor with capacitance equal to 5 by 6 farads. But something else is given, because VCT is shown. Let's see, in the circuit shown, switch SW is closed at t equal to 0. Assuming 0 initial conditions, the value of VCT in volts at t equal to 1 second. That's the only thing. There is nothing is stored initially. So it charges to the maximum voltage possible, and then just as we had in the early case, the time limit is 1 second. Okay, so let's see how it goes. Let's open out the capacitor for steady state purpose, and so we see that 10 volt is now shared between 3 and 2 ohms. So we have 4 volt and 6 volt as the share. So across 2 ohms we have 4 volt. Okay, so 4 volt is the building up voltage. So VC is equal to 4 into 1 minus e raised to minus TRC, as we saw. Okay, and now to find out R, we short circuit the voltage source, which is 10 volts, and we see that because the switch is already made, if the switch is not there, it would have been only 2 ohms. Now 2 and 3 in parallel gives you 2 into 2 to the 6 by 5. Okay, yeah, 2 to the 6 by 5. Okay, and so we have 4 into 1 minus, and so 6 by 5 is the resistance value, and 5 by 6 is the capacitance value. So together they make a time constant equal to 1. Okay, so e raised to minus t by 1, and t is equal to 1. Okay, that's what is asked. So t is equal to 1. So it is the same as equal to 1 minus e raised to minus 1. Okay, so this is a very important quantity, e raised to minus 1. It's the same as equal to 0.367. So 1 minus e raised to minus 1 is something that you can remember forever. It's equal to 0.632. Okay. So that's so 4 into 0.632 gives us 2.528 as the voltage across the as the voltage built up across the capacitor in 1 second. Okay, so yeah, so these problems are very simple so long as the three important aspects are understood. One is what is time constant. Okay, what is the current time constant after the switching. Okay, second is it charging or discharging. Okay, and okay, so what are the final values or the initial values. Okay, so all these things put together. Okay, finally is the charge being built up or are the charges being depleted. Okay, so or in the opposite direction. So perhaps we will have one problem of that kind here. What do we have here? In the fourth problem, the switch SW shown in the circuit is kept at opposite. Okay, so what do we have here? We have V01 and V02. Okay, they are supposed to be in the same direction, though it was wrongly marked in the some of the question papers. And then we are having a switch. It's a toggle switch which toggles from 1 to 2. Okay, and right now it appears to be on 1. Okay, and then there's a resistor R and a capacitor C, and VC is shown across capacitor. The switch SW shown in circuit is kept at position 1 for a long time. What does it mean? When it is kept at position 1 for a long time, it has already been charged. The capacitor has already been charged to what? To the total voltage that is available, because it opens out, so it gets the complete voltage. There's no current flow through R, so VO1 is or V01 is completely available across the capacitor C. Okay, at t equal to 0 plus, switch is moved from position 1 to position 2. Okay, assuming VO2 is greater than VO1, the voltage VCT across capacitor. Okay, if they happen to be in the same direction, there's a mistake. So, but things are all right, because we see that for one thing, the tau now is given by, that is the time constant now given by R into C, but where R is equal to, okay, the new circuit has to be taken into consideration. It's not RC, it is 2R plus C. Okay, sorry, 2R and C. Okay, 2RC. Okay, so tau is 2RC, and then you are having one voltage being superimposed, which is V02. V02 into 1 minus e raised to minus t by tau, the same tau, which is 2RC, and the other is V01 into e raised to minus t by RC. So that's how it has to be. But so certain mistakes are there, including there's no 2R. So I just put it here. But of course, these two things need to be taken into consideration. If they are in the same direction, they charge in the same. They charge and discharge in the same direction. So both V01 into e raised to minus t by RC, as also V02 into 1 minus e raised to minus t by RC will be positive. They'll be added together. On the other hand, if charging happens in the opposite direction, then charging or discharging, then one of these two quantities will be negative. Okay, and if the direction of VC is given, then whatever is the direction of VC will be chosen for finding the positive value. Okay, positive of the two. Okay, so I'm not detailing it, but of course the mistakes are enabling us to learn more. Okay, so I put it as it is. Going to the fifth problem. Here it looks a little congested because we are having two sources, 10 volt on one side, 5 ampere on the other side, and then we are having a capacitor in between, which is across the 2 ohm resistor in the initial case, where the switch is actually moving from and the 2 position where the switch moves to has now 4 ohms and 2 ohms and 2 ohms. Okay, this is a very good problem in the sense that there are quite a large number of concepts that we have already learned, which you can apply nicely here. Okay, so what all do we have here? So how do you proceed? Okay, first and foremost, as is written on the side, we need to find out what was the condition before. Okay, what was the earliest steady state? Okay, so the earliest steady state, and the question is also the switch has been in position 1 for a long time and abruptly changes to position 2. Okay, so if time t is in seconds, the capacitor voltage VC in volts for t greater than 0 is asked. Okay, and all the values have exponential quantity, so we will come to that soon enough. Okay, so first and foremost, let's see what was VC when the switch was in position 1. Okay, so of course the other part is absolutely away from everything, and so we are having 10 volt being shared by 3 and 2 ohms. Okay, so of course it has now 4 volt across the capacitor when the switch starts to move. Okay, and the capacitor now looks into a circuit which has several resistors and also a current source. Okay, so VC0 is equal to 4 volt is first. Second is of course what is going to be the steady state voltage across it. Okay, so if the steady state voltage needs to be found out, here we need to remember that the 5 ampere source passes through that inconsequential or irrelevant 2 ohms, and so you remove the 2 ohms, and so you see that now 5 amps is in parallel with 2 ohms. Okay, if you can accept this, this will enable you to do the problems in a very quick manner. Okay, so remove the 2 ohms but retain the 2 ohms in parallel with it. So you see that now it's the same as equal to a 10 volt source, 5 into 2, 10 volt source. Okay, so this 10 volt is what is going to come on as charges onto the capacitor of 0.1 farad. Okay, so we see SS, steady state voltage, is now 10 volt by virtue of our understanding that the first 2 ohms can be removed. So the in series with the current source can be removed. So the other 2 ohms in parallel with 5 ampere produces a voltage or gives a source transformation as given by 10 volts with the 2 ohms above it. Okay, or we are having 4 plus 2, 6 ohms. The other 2 ohms is completely removed. Okay, so now we are having this 10 volts being deposited on the capacitor as charges. Okay, so now we come to the time constant, and time constant for the right part of the circuit is alone valid because the left part is completely removed from our consideration by virtue of switching. Okay, so what do we have there? We look from the capacitor's point of view. We open the current source because it's not going to be relevant. So the capacitor sees only 4 and 2 6 ohms. Okay, you can have this as it is, but you can also have it as a source transformation. So 4 and 2 6. Okay, so 0.1 farad and 6. Okay, so 0.6. Okay, so 0.6 is going to be the time constant, and in almost all of the answers you see that it is T by it's T by 0.5 as also T by 0.6. So C or D may be right. Okay, so now what do we do? So now we write out the situation. What do we have? We have a situation wherein the positive terminal tells us that the positive terminal of the capacitor tells us that both the voltages, okay, both the deposited voltage which is now discharges as also the going to be deposited voltage which is 10 volt, it will also be charging the capacitor in the same direction. So the connection is going to be positive, that is of 4 into e raised to minus t by tau or 0.6 is going to be added to 10 into 1 minus e raised to minus t by 0.6. Okay, so just settle them together. You are seeing that there is only one constant which is equal to 10, and then you are having minus 10 e raised to minus t by 0.6 and plus 4 e raised to minus t by 0.6. So it's going to be minus 6 into e raised to minus t by 0.6. Very simple, but this 2 or 3 important things was spoken about. That is, the same procedure has been adopted. What was the initial steady state? Okay, and so we have a capacitor and it gets charged and then it discharges. Okay, so the direction is important. Okay, so it discharges from the positive terminal. So we are having 4 into e raised to minus t by RC. Okay, or t minus. Okay, so what is tau? Okay, of course you have to open. So when the new circuit is made, then that circuit gives rise to tau. Okay, so you open out the current source and you see that the capacitor sees that 4 and 2 ohms are in series. Okay, so you are having 1 by RC is the same, is equal to 0.1 into 6. Okay, so 0.6. Okay, so now we are having the final steady state voltage that's going to come on to the capacitor by virtue of the current source 5 amps. Okay, so there the 5 amps. Okay, even you can process it in a different manner because if the capacitor opens out, then the current flows through the 2 ohms and then it cannot flow through the 4 ohm resistor because the capacitor is open, so it will flow through the 2 ohm resistor. So 5 into 2, 10 volts. Okay, and the upper terminal is positive. Okay, so in all cases the upper terminal of the capacitor is also positive. So 10 into 1 minus e raised to minus t by tau. Okay, so very simply all the concepts fit together. That's the reason why you can't make mistakes in transients so long as you understand it appropriately. Okay, so moving on to 6th problem. Assume that the circuit. Okay, so again what do we have here? 12 volt source, 1 ohm resistor, then 3 farad and 2 farad, then a 2 ohm resistor in the center through which current IT is flowing, and then 2 ohms and 3 ohms. Okay, so there is an initial steady state wherein the capacitors have opened out, so IT becomes equal to 0. Why? Because the capacitors have opened out, so IT does not have a route to go back. So the current will flow from 12 volt source through a 1 ohm, 2 ohm and 3 ohm, that is 3 into 5 and 6 ohm. Okay, clearly because we are now going to have 2 amps, and so 2 amps will create 4 volt across 3 farad capacitor, and 2 into 3, 6 volt across the 2 farad capacitor. Okay, so this is the initial condition. But let's read the problem. Assume that the circuit in the figure has reached the steady state. Okay, so this is the steady state that we talked about before time t equal to 0. When the 3 ohm resistor suddenly burns out. Okay, so now we are having a different thing. That is, we are not having switching, but a resistor is burning out or changing the circuit, and so we are having a transient. Okay, resulting in an open circuit. The current IT in amperes at t equal to 0 plus. Okay, so what is going to happen? Okay, so now the bottom part of the circuit is isolated, no doubt about it, because the capacitor now needs to discharge. Okay, the capacitor already had 6 volts. The 2 farad capacitor at 6 volts, which it will try to discharge. How will it discharge? It will discharge via the 12 volt source, 1 ohm source, and when it comes to the capacitor, it will see a short circuit, so it will not follow the path of 2 ohms. Okay, because the 2 ohms path need not come to it, because it finds an easier circuit there. Okay, because it definitely has to flow through 1 ohm resistor. The 3 ohm resistor is gone, so 1 ohm resistor, and then it comes to the 3 farad capacitor, which is because of the transient situation, it has shorted out, so it flows through that, and then it goes back to the 2 farad capacitor. Okay, so that's one part which has been removed, which does not contribute to IT. On the other hand, the 3 farad capacitor, which had 4 volt across it, now discharges through the 2 ohms and 2 ohms, 4 ohms, such that it can return. Okay, it cannot flow through 3 ohms because 3 ohms resistor is burnt out. So you have 3, that is 4 volt divided by 4 ohms is equal to 1 ampere. Very simple, but at the same time the concept. Okay, the transients are beautiful in the sense that everything is perfect except for the fact that perhaps we don't have an understanding. I hope the understanding is appropriately conveyed, and I have written almost everything there as in step by step. But then things come very quickly for transients, because transients is a what do you say? It's a cauldron of concepts. Okay, so moving on to the 7th problem. A resistor, and when you are having something to read, then it takes some time, and so you have slowly got to write or read or draw something. A resistor and a capacitor are connected in series to a 10 volt DC supply through a switch. The switch is closed at t equal to 0. Okay, so we have two resistor and a capacitor, and then a 10 volt supply, as we have been seeing so far, and the switch. Okay, the switch is closed at t equal to 0. So the capacitor is now getting charged. The capacitor voltage is found to cross 0 volt at t is equal to 0.40 tau. So what's happening? So the capacitor already had some voltage, and that voltage is reducing because it is discharging, and so we are having two processes coming together. One is discharging and then charging. Because they are in opposite directions, what is happening is that the voltage is going to go down to 0 at 0.4 tau. Okay, what is tau? Okay, so all those things are going to be important. Tau is the circuit time constant. The absolute value of percentage change required in the initial capacitor voltage. So there was an initial capacitor voltage. Now it needs to change if the 0 crossing has to happen at t is equal to 0.2 tau. This is a very interesting problem in the sense that automation can be created. Okay, when do you want the voltage to go to 0? That can be created by simply charging the capacitor accordingly. Okay, so many things can be done via the understanding of transients. You can create circuits, you can do some automation, you can do many things. Okay, so now here we are having two situations. One is that there was an initial voltage across the capacitor, and that is discharging, while you are having the charging also happening, and then they are being equated at t equal to 0, at V is equal to 0, or the voltage equal to 0 at t equal to 0.4 tau. But now you want something else. You want more voltage, or you want some another voltage to be introduced into the capacitor, such that more voltage to be introduced to the capacitor, or more or less, let's see, such that now it discharges even faster. That is, it discharges to 0 at t is equal to 0.2 tau. So it definitely so there is a reduction in voltage. Only then the reduced voltage discharges very quickly, and that too in t is equal to 0.2 times the tau. Okay, so let's write out whatever we understand. We understand that there is a charging happening. Okay, as we said earlier, 10 into 1 minus e raised to minus t by tau. Okay, minus t by tau, but then that's happening, but t is equal to 0.4 tau, because at that time we are seeing that the voltage is equal to the discharge value. So what is the discharge value? So earlier, if the capacitor was charged to V1, so V1 into e raised to minus the same time. So e raised to minus t by tau, where t is equal to again 0.4 tau. Okay, so this gives you first equation, and then what is required out of you is that, okay, a change of situation wherein all these things need to happen together. Okay, it need to happen in a lesser time, which is equal to 0.2 tau. Okay, so it's the same equation except for the fact that 0.4 is replaced by 0.2 and V1 is replaced by V2, because now we are talking about another kind of voltage, that is to which the capacitor is charged such that discharge happens faster. Okay, so now we are having two equations. You can take the ratio. Okay, and once you take the ratio, you see that V2 by V1 is equal to 0.45. Okay, so everything, okay, since all the details are given here, and it has been, I hope it has been explained appropriately, then you can just substitute for all the values. Okay, so especially e raised to minus 0.2 and e raised to minus 0.4. Okay, so that's all that you got to write, because tau cancel, and then you see that V2 by V1 is equal to 0.45. Okay, of V2 is only 45% of V1. Okay, so or in other words, there is a reduction. Okay, so the absolute percentage change is now going to be 55%. Okay, and it's negative. Okay, yeah. So yeah, moving on to the last problem in this section, we are having three capacitors. Two of them are in parallel. So when you are having parallel capacitors, the total is equal to 0.3 plus 0.5, 0.8. And then in series, which means that 0.8. Okay, so don't make mistakes about capacitors when compared to resistors and inductors. Okay, so when you are having them in parallel, add them. So 0.8. Now when you are having them in series, 0.8 into 0.2 divided by 0.8 plus 0.2. Okay, 0.8 plus 0.2 is 1, and 0.8 into 0.2 is equal to 0.8 into 0.2 divided by 0.8 plus 0.2. Yeah, okay, so that's equal to 0.16. Okay, so 0.16 is the capacitance, and you also have, let's see the situation, 100 volt on one side, 10 kilo ohm. Okay, and the switch seems to have been at A, and then it's pushed to B, such that now the whatever is charged in the capacitor discharges through the 5 kilo ohm resistor, and 10 kilo ohm resistor is discarded. We don't look into that direction at all. Okay, but 10 kilo ohm is important for charging the capacitor. So what is the capacitor charged to? Okay, before that, let's read the problem. The switch in the circuit shown was on position A for a long time and is moved to position B at t equal to 0. The current IT for t greater than 0 is given by. So the current is asked. Okay, so though we always calculate in terms of voltages, we can definitely go for the current as well. Okay, so what's it now? So what was the earliest steady state? The earliest steady state was when the capacitor was open, was that the entire 100 volt becomes available across it. Okay, so the capacitor is open, so capacitor is the capacitance value is equal to, as was mentioned earlier, 0.16. It's all microfarad. Okay, not simply farad. Okay, and VC is equal to 100 volt. After switching, tau is equal to RC. Okay, so we are having 5 into 0.16. Okay, and 5 is kilo, and 0.16 is micro. So together we are having 0.8 milliseconds. Okay, and VC discharges through 5 kilo ohms as IT. Okay, so what is IT? We are having VC by that is the voltage that is available, which is 100, divided by the resistance 5 kilo ohms. So 100 by 5. So you write milliamps, then you raise to minus t by tau, where tau is equal to 0.8 milliseconds. So that works out to be minus 1250 t, and the answer given is 100 by 5 is 20. So we are having 20 into e raised to minus t minus 1250 t, so many milliamps, and ut just tells us that at that point of time it happens. Okay, when the switch is converted. Okay, so today we have been looking at in this session we have been looking at some of the aspects that are very important for capacitors. Okay, the capacitor is always capable of charging as much as is possible, but if the time limit gets over, it will charge only to that particular value of voltage, or there are so many charges only, because if the time ceases to connect between the source and the capacitor, then the capacitor can have no more charges. Also the voltage may be lesser, as we saw in the earlier case. Okay, we also saw a particular case wherein we saw that the initial conditions are going to be very, very important. Okay, so if the initial conditions tell us that the capacitor is charged to a particular voltage, then that voltage has to discharge and the new voltage has to creep in. Okay, so if both of them are the same direction, then we don't have a problem because they can both be added together. It's actually talking about a charge condition. So the charges are filling at the same time, some of the charges leaving. That's all. Okay, but on the other hand, if the voltage is, if the capacitor is being charged from the opposite direction while it is discharging from another direction, then you are going to have an opposition between the two, or there's going to be a subtractions or minus sign. Okay, and on the other hand, if you are having so that also we saw such an example also. So on the other hand, if you are having a situation wherein you require a situation wherein the complete capacitor has to discharge, okay, in a particular time, okay, such that you can have zero voltage. Okay, you can call it as a zero crossing point. Okay, so then in that case you have to plan it appropriately and you have to place sufficient charges on the capacitor such that this process happens, as we saw in the last problem, wherein we saw that we are having 10 into 1 minus e raised to minus 0.4 tau by tau, or minus 0.4 is equated to V1 into e raised to minus 0.4. Tau by tau is V1 into e raised to minus 0.4. Okay, because in 0.4, okay, so we already know the time constant and we plan for it to be discharged at 0.4 times that particular time. Okay, so that is one planning that you can do. But on the other hand, if you want to change it, okay, for another situation, then you have to charge it to a different voltage. As we saw earlier, it has to be V2. Okay, such that 10 into 1, the same old 10 into 1 minus e raised to minus 0.2. Okay, tau by tau gets cancelled, is equal to V2 into e raised to minus 0.2. Tau by tau, they get cancelled. Okay, so now we know that we have a ratio between V1 and V2, and we can see that, or V2 by V1, and we can see that, okay, so there is a reduction of voltage because the capacitor has to discharge quicker or faster. Okay, so these are some of the things that we have learned. I hope the whole session has been useful for you, especially to understand transients in a beautiful sense, because transients and the concept of transients seems to be one of the most beautiful concepts in electrical engineering, and if you internalize it, electrical engineering becomes very simple. Thank you.